So I'd like to join all of the other speakers in thanking the organizers, the chair of my session, but the organizers for organizing this amazing conference and for including me in this sort of amazing list of talks and speakers. I'm really very honored. But I thought you might be getting tired of all of the thanks and praise, so I'm going to give just a little tiny bit of constructive feedback. So, one of the things I've really enjoyed actually is just exploring a little bit around the area. It's hard because there's so many good talks, you can't go very far, but I've been walking around your beautiful campus and I've seen a lot of, let's see, this is not, there we go. A lot of these banners around the thing, around campus, and I have to say I actually really like the top part, known as an invitation to explore is great, but I feel that defy gravity as a physicist, I'm not sure how I feel about it. So I'd like to propose a modification. You can, okay, so anyway, you can take that to your deans or whoever's in charge of these things. Okay, but so I'm going to talk today about a test of gravity, and so and what I mean by testing gravity is really testing relativity. So why do tests of relativity at all? Well, I think I don't need to tell all of you, both quantum mechanics and general relativity are, two cornerstones of the Standard Model, and they've been remarkably successful, right? Both of these theories, pass every test that we can throw at them with flying colors. And recently, in the case of general relativity, with LIGO now, we are measuring gravitational waves from truly just, catastrophic events, things that at least my mind cannot even grasp, where you have, black holes that are 10 times the mass of the sun, moving at relativistic speeds around each other and then merging and radiating out more energy in gravitational waves than the mass of the sun. And yet still somehow general relativity describes it, as far as we can tell, perfectly. And on the other hand, I think in an atomic physics conference, I don't have to convince any of you that quantum mechanics so far is pretty good, right? And but the problem, as I'm sure you're all aware, is that we don't know how to combine these two things. There is no currently, unified theory of quantum gravity. We heard a beautiful talk from Monica Schleyer-Smith on Monday about starting to explore directions like this, but I think it's still very early days of trying to build these theories and test them. And so instead, where I come from is to actually try to continue to test general relativity, to push it and probe it, and maybe find areas where it's weak. That's obviously very hard given all of its success, but a natural place to explore how these two things mix is to actually use quantum systems to test relativity. So at the heart of the theory of relativity is the Einstein equivalence principle that basically says that these two scenarios, being on Earth and just sitting stationary in Earth's gravitational field, and being with local acceleration due to gravity little g, and being in space in an elevator that's accelerating at acceleration a, if a equals g, we can't tell the difference if we're inside of these elevators. And this is really at the heart of general relativity. In general, this is not tested directly. Rather, we do tests of three different sort of principles that, when combined, give us general relativity. So there's the weak equivalence principle, which is just that different things of different mass, fall with the same acceleration. There's tests of local Lorentz invariance, that it doesn't really matter in an inertial frame what the velocity of the inertial frame is. And then there's tests of local position invariance, and we heard a beautiful talk from Eckhard Pike on Monday about how to do tests of position invariance by actually comparing different frequencies and different atomic transitions in ytterbium clock ions. But there's another way to test local position invariance, which is to do tests of the gravitational redshift. So you're likely all also familiar with the gravitational redshift. The idea is that if I have a clock, if I have two clocks, and one clock is higher than the other clock in a gravitational field, it has a higher gravitational potential, then if I try to compare them using light, as I send the light up from one clock to the other clock, it gets shifted. There's this redshift as I go from the lower clock to the higher clock, and so this lower clock will sort of appear to be ticking slower than this higher clock, and that shift that you measure is just proportional to the local acceleration due to gravity, g, times the difference in height divided by the speed of light squared. And so, this was a prediction. Initially, tests were done by looking at solar spectra and things like that. But then, in a really groundbreaking experiment using Mossbauer spectroscopy, Pound and Rebka were actually able to measure this effect at a height of 22 meters at Harvard. And, this was a truly remarkable test. And just as a comment, this is really cool. You can still see the actual notebook that Pound originally wrote this, did the math and wrote this result. So for the young people in the audience, this is what Jupyter notebooks used to look like. So you can actually see down here at the bottom, this is, boxed just like one of in an education instructional lab, the answer at the bottom showing the Einstein value and showing that it agrees, which is really pretty amazing. When I showed you this diagram, I showed you two clocks, and Mossbauer spectroscopy is a little funny because you don't actually know anything about the frequency of the gamma rays, or very little about it. Instead, you're just measuring relative shifts, and so it's natural to try to do these experiments not with gamma ray emitters, but rather with atomic clocks. And so this was done in 1980. There was Gravity Probe A, where they put a hydrogen maser on a rocket, and they compared those two clocks at a height difference of 10,000 kilometers, and indeed measured what they expected. And for many, many years, this was the best limit on local position invariance and on sort of modifications to the gravitational redshift. But I like to do experiments in the lab, and so I'm not super interested in putting these experiments that I spend so much time building and working on a rocket. And so the question is there some way to do the same kind of experiments in the lab? And the answer is yes. We just need better clocks, and then we can see smaller redshifts. And the way that we can do that is by moving from microwave transitions, like the maser, the hydrogen 21 centimeter line that was used in the hydrogen maser, to optical transitions in more complex atoms. Like we heard a number of beautiful talks this morning about the alkaline earth and alkaline earth-like atoms, from Manuel and Adam. So we can do the same thing. We can take advantage of this more complicated structure of the alkaline earth atoms and use an optical transition instead of a microwave transition. And there was a beautiful experiment at NIST in 2010 where they did this. They actually took two single aluminum ion clocks in the lab, and my understanding is they just raised an optical table up a foot with jacks, and they were able to see from raising up one clock with respect to the other by a foot the gravitational redshift at 4 parts in 10 to the 17. Since then, there's been progress, and in optical lattice clocks, so ytterbium here, this is an experiment where in the Ludlow group, also at NIST in Boulder, they compared two ytterbium clocks with enough accuracy that they had to account for the 4 centimeter height difference between the two clocks in order to get the right answer for these two clocks to actually agree with each other, which is really pretty amazing. This is also, to some extent, kind of bad news now for doing clock comparisons and redefining the SI second and things like that, because what this actually means is that if you want to compare clocks between labs and across different standards institutes, now in order to do it at the accuracy that we think we can control these clock frequencies, you actually have to know their relative heights with respect to the Earth's equipotential at the centimeter level. And that's sort of a bit of a problem that we just have to deal with, but we can also maybe turn that problem into a feature, because if we don't have any good way of measuring relative height differences between different places on the globe, we can actually use now these clocks as that tool. And there's a lot of work going on around the world on starting to do this by building portable optical clocks and taking them around and comparing them across fiber networks. And later today, I believe you'll hear a talk from Professor Hidetoshi Katori on a beautiful experiment that they did in Tokyo where they compared two clocks in the Skytree Tower. And so this is another motivation, basically, to try to measure the redshift and to measure it at smaller and smaller scales, because we actually want to use it. People are actually interested in determining relative heights using relativity at this new scales with these clocks. I also mentioned the idea that we can maybe get something new out of using quantum systems to do this, and these atomic clocks, these optical clocks, are really becoming more and more quantum, I would say. We have better and better control over the states of the atoms in every sense, the motional states, the internal states. We'll hear talks later from Vlad and Vuletic about spin squeezing the states of these clocks, making entangled clocks, which are becoming more and more quantum. And so it's interesting to think about measuring the redshift with quantum systems. There was a very nice theoretical paper that talked about, if we want to try to combine gravity and quantum mechanics in the simplest possible way, we have to think about just how the Hamiltonian evolves, given that there's different rates of time in two different locations. And so if we take some particle that has internal states with an energy difference delta E, and we do matter wave interferometry, just like the last very nice talk that we heard. We split it in two, and we put it in a spatial superposition, and we put one half up here and the other half down here, and then we recombine them. We can look at the fringes from that matter wave interference, and if the two paths are in the same state, that's fine, then this particle doesn't know which path it took. But if it was in a superposition of these two states, well, this is now a clock, and that clock can in principle tell which path it took. And so you could now have a situation where at certain times the visibility of your interferometer, meaning whether or not you see interference fringes, will just disappear. And that's what this visibility parameter here is showing you. And this is not exotic physics. This is not some gravitational induced wave function collapse or anything like that. This is just the simplest possible way that you could try to incorporate our understanding of general relativity into quantum mechanics. So this is a really interesting direction to go, and to do this we need to kind of start to be able to measure the redshift at the same scale that we can do these kind of matter wave experiments. Okay, and so with that as motivation, basically we can draw a line looking at how the performance of clocks have improved over time, and we can say, okay, we're just starting to enter this regime where we can't measure height differences any other way, so we can use these clocks to measure these height differences. We can also start to measure things at scales where we can produce spatial superpositions. So let's go ahead and do it. And so in my group at Wisconsin, we built an strontium optical lattice clock. Okay, you can see here, this is the CAD drawing of the apparatus. This is an actual picture of it with a strontium mott in here, this nice glowing blue ball. And that is a cloud of strontium atoms trapped in a magic wavelength optical lattice that we can actually use as our clock. Okay? So that sounds good, we're ready to go. There's two problems though, right? One is I need to do a redshift, I need two clocks, okay? And I didn't have enough grad students or enough startup funding to build two strontium clocks, so that's one problem. And then the other problem is when I actually look at the performance of this clock, I purchased a very nice ultra-stable clock laser with this 12 centimeter ULE cavity from Menlo Systems. This is a very nice turnkey system, and this is the kind of system, it's rack mounted, so it's the kind of system that we might want to put eventually in space or on trucks and move them around to do portable measurements. But unfortunately, as a result of this being not the cutting edge best laser in the world, when we probe our atoms with this clock laser, we get a Rabi line width of about 10 hertz, or correspondingly, when we do Ramsey experiments, we see a T2 start time of about 100 milliseconds, okay? And so when we plug in the numbers for our clock, the dead time, the coherent interrogation time and everything, we get an expected stability of something like 4 times 10 to the minus 16 per square root hertz in terms of our ability to measure, if we were doing a comparison between this clock and another clock that doesn't exist. June, whenever I meet up with June, he always talks about how we need to run a fiber from Wisconsin to Boulder in order to do these comparisons, but we don't have it yet. So anyway, we can just look at the numbers now. Suppose we wanted to measure at a centimeter scale with two clocks like this. For a 1 centimeter height difference, that's 1.1 times 10 to the minus 18 in terms of the redshift. That's about 43 hours of continuous averaging. That's maybe sounds to some of you who work on precision measurement reasonable, if hard, right? But I'm interested in going below the centimeter scale. If we plug in 1 millimeter, now we're at 185 days of continuous averaging. This is not scaling very well, and it doesn't sound very feasible. And maybe more importantly, this is just statistical uncertainty. It doesn't include the systematics, right? And to get down to that level of sort of systematic accuracy, I often have to measure my systematics for much, much longer than I actually average down my statistical signal. So this is starting to sound really impossible. But of course, when I built this experiment, I foresaw these difficulties, and so we're going to take inspiration from other experiments to get around this. And in particular, we just heard a beautiful talk about measurements of the fine structure constant with atom interferometry. This is a figure from the paper from Holger Mueller's group at Berkeley, where they did the previous measurement with cesium. And you can see that they actually use two conjugate Ramsey-Bourdet interferometers, and they do a differential comparison between these in order to cancel out sensitivity to things like accelerations. And similarly, LIGO actually uses a Michelson interferometer. It doesn't just use a single arm and try to measure the frequency shifts due to gravitational wave. That would never work. It uses a Michelson interferometer and does a differential comparison between the arm lengths in the two arms, and that cancels out laser frequency noise so that you can get a very nice, very sensitive measurement of differential changes in length here. And so we're going to do the same thing. The idea is, rather than having a single clock in our experiment, we're going to have two clocks trapped in one optical lattice, one down here and one up here. and we're going to shine the same clock laser on both of them, and we're going to do differential comparisons between them. And this will be really nice because it should cancel out clock laser noise. It should make us insensitive to this, the laser noise that I already told you about that's kind of limiting our sensitivity. And also, these two clocks are in the same environment now, and so they're sort of experiencing a lot of the same environmental perturbations that give you the systematic uncertainty, so hopefully we'll also do better in that regard. So I want to say that this is not a new idea. There are a lot of other beautiful differential clock comparisons that have been done by groups all around the world, including a number of people who you've already heard from, and Dave Librand, who you're going to hear from later this week. Okay, but so we're going to do that. How do we actually make this double clocks? Well, what we do is we load one region of our lattice, and then we move our lattice. We just make it a moving walkway, basically, or a conveyor belt, and then we reload in a new region of the lattice. So this is actual camera images from our experiment. Just there we turned off our second stage cooling MOT, and you saw the atoms fall. And then we shift back down, so these two now regions of atoms trapped in our lattice are symmetric with respect to our lattice beam waist. Okay? And so now we can just be ambitious. We can try doing a really long Ramsey interrogation time. We can probe for 8 seconds, which is well beyond the 100 millisecond coherence time that I showed you for Ramsey. And as you can see, if we just look at the outcome of a Ramsey experiment with a single cloud, we just get noise, right? This is exactly what you would have expected. Basically, what this means is the phase of the second pi/2 pulse is completely random with respect to the first one because we're probing well beyond our laser coherence time, right? But we have two regions, so we do the same experiment with both simultaneously. We plot the outcomes, and you can squint at this and maybe see that there seems like there's regions where there's more white space for both. These points are kind of seem like they're maybe correlated some way, but it's hard to tell. So we can, again, take inspiration from what the atom interferometry community does, and we can look at this data a different way. We can plot it sort of parametrically, or in what's called the Lissajous style plot, where we plot the excitation fraction of region 1 on the x-axis, excitation fraction of region 2 on the y-axis, and I'm just going to show you the data coming in one point at a time and plot it on this plot, right? And so the same exact data I showed you before is up there in the left-hand corner, and now when I plot it in this way, you can see that it fills out this very nice ellipse, right? Every single point here lies on this ellipse, and we can actually fit to this ellipse and get the frequency difference between these two clocks now without worrying at all about our clock laser and what it's doing, and without really gaining any information about the clock laser frequency. So why, just for people who haven't thought about this before, why is that the case? Well, actually, all that's happening is I'm doing two Ramsey experiments. That just gives me these two cosines, and then I have the phase of my laser, theta L, and that's random shot to shot. And then I have a phase difference between my two clocks that's proportional to the frequency difference between the two clocks times the interrogation time. And so you can see, obviously, if this frequency difference is 0, this phase difference is 0, these are just going to be on top of each other, and I just get a nice line, right? If it's pi/2, then I have this style of situation where I'm just randomly sampling points on these two cosines that are phase shifted, and then I actually get a circle. And if it's pi out of phase, then I get an anti-correlated line going the other way. So by fitting to these ellipses now, I can actually learn a lot without being limited at all by my laser performance. And you can see that here. So we went from 96 milliseconds when we do traditional Ramsey to when we look at these differential comparisons via an ellipse. Here I'm plotting the contrast of this ellipse that we extract from fitting to it. You can see that we now have 26-second coherent interrogation time with this, not so amazing clock laser. Okay, and that allows us to really get very high stability now clock comparisons. So differential clock comparisons, you can see here that we just took one ellipse and we averaged for a few hours, about 3 hours. We have about 2,000 atoms per region. We're interrogating here for about 8 seconds. And you can see we're averaging down on this Allen deviation plot, and we have a stability now of just below 10 to the minus 17 per square root hertz. So, more than an order of magnitude better than what we would do with an individual, comparing two independent clocks. And here, after 3 hours, we average down to below 1 times 10 to the minus 19. Great, thank you. So I want to mention that in parallel, June's group was doing similar styles of experiments, but with a single region, so an extended region, and they were looking at comparing different parts of this region across a millimeter. And they got even more impressive results. They were able to get to 4.4 times 10 to the minus 18, so better than a factor of 2 in stability, and they averaged for quite a bit longer, and actually got, amazingly, they got down to below 10 to the minus 20. So they're now measuring frequency differences at 21 digits of precision, which is really, truly remarkable. But one comment, they were using a really beautiful cutting edge, the world's best clock laser with an 8 millihertz line width. And so I think it's significant that we're able to get kind of comparable level of performance with a much worse laser that we can maybe make portable and things like that. And in addition, we've continued to make improvements on our experiments, so we're now pushing down towards the same level of performance that June and his group were able to demonstrate. So the best we've seen so far is about 7 times 10 to the minus 18 per square root tau. Okay, so I just want to mention, this is actually, if you think about it, sort of a modern Pound-Rebka style experiment. Because now, just like in the Mossbauer spectroscopy case, we're not learning about the frequency of our clock laser, which is actually the clock in most optical atomic clocks. The laser is the clock, right? We're only learning about frequency differences, just like Pound-Rebka. And so this is not an absolute clock measurement. You can't use this to redefine the SI second or something like that, but you can use this style of measurements to do, say, gravitational redshift experiments. And that's what we're going to do. We can do, though, some things that Pound and Rebka couldn't. One thing we can do is we don't have to stop at just 2 regions. So we can load now multiple regions. Here, this is, again, camera images from our experiment showing how we load 6 regions. Okay? And now we have kind of a miniature clock network, because if you think about it, we have, in this case, so in the end for these redshift measurements, we wound up doing 5 ensembles, not 6. I don't have a nice animation of 5, but the reason for that is it was nice to actually have a single ensemble right at the center for doing kind of asymmetric comparisons and learning about exactly what's happening at our beam waist. Okay? But so we have this now network where we're simultaneously doing comparisons pairwise comparisons between every one of these clocks, and so that's 5 choose 2 or 10 of these ellipses that we get out simultaneously as we take the data. And this is actually quite nice for doing redshift measurements, because it means that we get information about this separation between the 5th and 1st clock, which are separated by 1 centimeter here, but we also get at the same time 4 runs that are telling us about the gravitational redshift at 2.5 millimeters, and we have 3 at half a centimeter and 2 at 0.75 centimeters. Okay, and so now you can see actually, if we wanted to measure the redshift between these clocks that are separated by 2.5 millimeters, at the stability that we're now achieving for these differential comparisons, we're actually only talking about 30 minutes of averaging instead of many days, right? So we're doing a lot better. But as I mentioned before, you can't just talk about statistical uncertainty. You have to talk about systematic uncertainty. We have to characterize all of the systematics in our apparatus. And now the systematics are a bit different than the traditional optical clocks, because we only care about differences between these ensembles, and they're in kind of a similar environment. And in addition, we get to use these differential comparisons as we do all of our systematic evaluations. And that's huge, because it allows us to average down on these systematics really very fast. And so just to give you an example, we can measure the density shift. And the way we do that is just by changing the density in one region. We load one region for longer compared to another, and we make a large lever arm that we can use to learn about the frequency difference of these regions, and we can change which of the 2 regions we loaded with higher density and do all of the kind of checks that you would expect. Okay, it turned out one of our biggest uncertainties, and this is maybe not surprising to those of you in the optical clock community, is the thermal gradients across the chamber. So I naively thought, look, these 2 atoms, these ensembles are only a centimeter apart. They're seeing the whole same black body environment, right? How different can it really be? That turns out to be wrong. We have thermal gradients across our chamber. We have water-cooled Mach coils and things. The temperature is just a little bit hotter on one side of our chamber compared to the other, and these atoms are just closer to this viewport than they are to this viewport, and vice versa for the atoms on the top. So what we found when we changed the temperature of one viewport compared to the other, we just introduced larger gradients, we could actually see large linear shifts across this array of ensembles. But fortunately, we can introduce much larger gradients than we have naturally, and we also have calibrated temperature sensors on each viewport so that we can back out and correct for this shift. Just to comment, what this tells you actually is if you are doing these optical clock experiments and you have a 1 Kelvin difference between the top and bottom of at least our chamber, right? This is going to depend on the geometry of each individual chamber, but in our scientific chamber, if you have a 1 Kelvin shift across the chamber and you move your atoms by just a centimeter, that's the only thing you change, you get 4 times 10 to the minus 18 shift, right? So this is exactly why clock measurements are really, really hard. Okay, so we did it. We did a full systematic evaluation. Here is our systematics table, our error budget. And you can see that I'm not showing you the answer. The reason for that is because we did this whole thing blind. We blinded our data using our analysis software so that we couldn't bias ourselves to the right answer. And so what this means is we basically decided all of the numbers in this table before we removed this offset that we didn't know what the value was. So I want to do that for all of you. Here's what our data looked like as we were analyzing it and as we averaged down, okay? And this green region is the range of possible values of the blind. And the black 0 would be there's no redshift across the sample. The black line is what we would naively expect. And when we removed the blind, I was very relieved to see that it agreed within our within our systematic uncertainty. You can see if we zoom in here, this is what that looks like, okay? But I want to show you the data also a little bit of a different way. So here you can see by separation. So because now we're doing these measurements with regions separated by 2.5, 5, 7.5 millimeters, and 1 centimeter. And we can actually see the redshift, very clearly in our data. The black line is what we would expect, and the red line is from our fit. And so you're all physicists, you know what a centimeter means, but for me it was helpful still to think about this with some reference. So a centimeter is the radius of a penny, so, half the diameter. And 2.5 millimeters is about the distance from Abraham Lincoln's beard to his tip of his nose. Okay, I realize, though, we're in Canada, so here's the Canadian penny. Queen Elizabeth doesn't have a beard, but from her chin to her nose, we're measuring the redshift across it. Okay, I'm very close to wrapping up. Okay, but I phrase this as a test of the redshift in the lab. So now we can look at our measured redshift, and we can characterize it in terms of, suppose we posited that there was some variation to the redshift from what we expect. People do this using this alpha term. This is unfortunate because this is not the same alpha you just heard about in the previous talk. It's just some constant that you're adding to change the scaling of the redshift so that it doesn't just look the way we expect it to, okay? And what we get is that alpha we can bound, to 0.14 plus or minus 0.23. So we're only testing the redshift to about a part in 4. Actually, this is similar to the original limits that Pound and Rebka set. If you look, though, at how these limits look compared to distance, what you're measuring the redshift over, we're in a kind of unique space over here where we're measuring this in an entirely new regime in the lab at the centimeter scale. I also want to highlight, I told you about the beautiful results from June's group. They also measured the redshift across a single cloud, a really amazing measurement. And what they also saw was consistent with what you would expect across this individual millimeter. But I'll say that I think one nice thing, again, about our measurements is that we now have these separate ensembles. We're doing measurements that are at least somewhat more similar to what you might use for doing relativistic geodesy, and we can view our data that way. We can think about what the minimum resolution is in terms of doing relativistic geodesy with these clock comparisons. And what we also did is we said, suppose we believe the redshift and we forget that we know what the height ordering looks like, and we just treat this as a network of clocks with unknown height. And then we use the measured redshifts that we extract independently for each pairwise comparison, and indeed we assign the right order to the height of the network, and we get pretty good agreement with our known splittings. Actually, all of the different pairwise differences in height are within 1 sigma of what we know the correct answer to be. Where is this going in the future? So Pound and Rebka actually, in 5 years, managed to reduce their systematics by an order of magnitude, and I think this was our first shot at this. We learned a lot from doing it. I think it's pretty clear we could do something similar, and in fact, June and his group were able to do better because they measured the redshift across a millimeter scale cloud. Their systematic uncertainty is about a factor of 10 below ours. So you could imagine, I think, doing something similar within, say, 5 years. Going forward, if you want to do something sort of, that's pushing the boundaries here, you could think about trying to build an experiment like this that's a meter scale separation between these clocks. Of course, the systematics are going to get harder, so it's a little bit ambitious, but if I assume I get the same systematics as this factor of 10 boost that I already just told you that I would get, even though I didn't do it, and I just assume that now I'm separated by a meter, then we're starting to push against competitive boundaries on the redshift, and we're also entering this really interesting region, and this is the last thing that I'll say, in terms of testing sort of quantum mechanics and relativity. So it might sound like we're pretty much here, except for that we haven't put our atoms in a spatial superposition. So I could say, suppose I didn't just separate different ensembles of atoms, but I did this experiment with the same ensemble of atoms and put it in a spatial superposition separated by a centimeter. Could I see this change in visibility when I recombine these two clocks? And the answer is no. So we're doing about 10-second coherent Ramsey interrogation times. Our atoms are separated by at most a centimeter. That's 27 milliradians phase difference. So Eric Cornell told us this is trivial to measure, okay? I'm not sure I entirely agree in this context. It wasn't trivial, but we were able to measure it, okay? But nature doesn't really care very much about a 27 milliradian phase difference between these ensembles. The visibility when you recombine these would still be 0.9999. Okay? However, if you did this experiment with 1 meter superposition and 10 seconds interrogation time, now you're at pi radians phase difference. And that's going to let you kind of test these kind of predictions. Okay, so I'm going to skip over the very last part of my talk and just...
Yeah, wind it up now, please.
I'm winding up, exactly. So this is the end. I want to thank the people who actually did the work. And especially I want to highlight... yes, so now my laser pointer doesn't work anymore because I did that. That's fine. So, so these are the people who did the work, and especially I want to thank Xin Zhang, the postdoc, who was really with me from the beginning and built this experiment from scratch with me. I want to say I'm looking for new postdocs and grad students, so if you're interested, please come talk to me, and I want to thank you all for your attention. And sorry for going long.
Yes, well, thank you very much, Shimon, for this beautiful talk, and I'm sure the Queen is smiling favorably on the proceedings. So, students, questions first. Give students the first chance.
Hello, thank you for the talk. I have just one question about the differential light shift in your in the clouds you have in your dipole trap, because that must be also something to account for in your measurements.
Yes, so I skipped over all of the systematic uncertainty, all of the different systematic things. I just gave you a couple of examples. Here is a slide that I skipped that I can now pull up for you. So I would direct you to our paper, which I should say was posted on the archive on Sunday night. And so the method section has detailed explanation of how we deal with all of the different systematics. The light shift is one of our biggest systematics. There's actually two different ways that it enters. One is that because of the finite beam waste in the Rayleigh range of our beam, these different regions are at different depths. And you can see that effect on the left-hand side here. But there's another effect that we found that we weren't exactly expecting, which is we actually see a linear gradient across our array that depends on the lattice depth. And what we think is happening here is we know we have a magnetic field gradient as well across our ensemble, and so there's a tensor light shift that actually changes depending on the orientation of the magnetic field with respect to the polarization of our lattice. But the good news is we can still just account for it, because what we can do is we can measure the light shift at a bunch of different depths across our array and then extrapolate down to, to 0 basically, and then plug in what our operating depth is. And so that's what we do. And again, we did all of this blinded, so it worked out that we think we accounted for this properly. But this is the kind of thing that you do have to deal with. Yes. Great question. Thank you.
Thank you.
Okay, Zhang Chao.
Okay, very nice talk. For the gravitational redshift formula, what you say, this formula doesn't care. The two frequencies are classical nature or quantum nature. Is there any
that's correct.
implication? Or?
Yeah, no, I mean, I think what relativity is saying is physics, is the same at these two different points, but time is, relatively speaking, different. And so every physical thing, quantum or classical, that happens up here will appear to happen at a different rate than the same experiment down below when you compare them. But locally, if you're at that height, everything always looks the same, right? If you compare an atomic transition to a physical thing, it'll always agree.
Yeah, time is just marking the progress of the system. It's not
yeah,
that's right. There's no quantum mechanical variable corresponding to time. Or operators.
It looks like there's a theory as quantum mechanics in curved space. Okay, if we derive from that theory, okay, is there any difference? Or
I mean, this is pushing my levels of understanding. My understanding is it depends, how you want to try to plug time in. But in the papers that I showed you from theorists who've been thinking a lot about this, they're just plugging the time into the evolution of the Hamiltonian, in that local frame, right? And that's all they're doing.
Yeah. Well, we'll have to end the proceedings in a very few minutes, so just perhaps one or two last questions. Yes?
Hey, thank you for the talk. For this talk, you talked about the gravitational redshift relevant to the small g. So I'm curious, is similar technique can be used to test the big G? For example, can it be used to test whether the gravitational force decays as 1 over r squared?
Okay, that's a really great question. I think I have to say I don't really know. But one comment I'll make is, of course, it's tempting to say now we're measuring an effective gravity on these very short length scales. Can we use this to probe whether gravity, varies, doesn't behave the way that we expect on those short length scales? And the thing I'll say is, in general, these are very poor measurements of gravity because these effects are suppressed by c squared. So we have to work incredibly hard to just tell that there's gravity in our lab at all when we do this measurement, whereas if we just dropped something, it would have been very easy. So, so atom interferometers and other ways of testing short-range gravity using MEMS devices and optically levitated nanobeads and things are probably a better way to go. Having said that, if someone comes to me and says, I have a theory where the force due to gravity doesn't change over short-length scales, but the redshift does, that's maybe something that you could think about trying to measure. Having said that, if you plug in the redshift that you expect from the largest, densest mass that you can put close to your atoms, it's really negligible, right? Our redshift is entirely dominated by the giant Earth below us. The potential is not really changing very much if I bring a mass next to it. And it's much easier to measure gradients in that potential, which is what like atom interferometers and things do, than it is to measure actually just a potential difference using these relativistic tools. It's a great question.
Okay, well, let's thank both speakers for 2 excellent talks.